everybody, Mr. Ribot here. Today we are looking at topic 314, a little pi action there, of polar function graphs. So, weird thing with polar compared to like rectangular is the coordinate points for rectangular is x comma y. X is your like your domain, your y is your range, right? Um, your independent versus dependent, where when we write the coordinate points of polar, it's actually switched. We write r first, comma theta, where theta is actually the input and r is the output, r being the dependent and theta being the independent. That's what this whole first part is talking about. So, you're not going to be required to necessarily sketch these by hand, but you will have multiple choice, right? They're only going to appear in multiple choice, so we got to make sure we understand how this works. And we're going to look at some of these choices. And one strategy is plug in values. There's nothing wrong with plugging in values. See if those values are on the graphs, but you just remember you're plugging in and you're getting polar values. Another way is just know how these graphs work. And so we're going to go through a few examples here. And they're really interesting graphs too, very different shapes than you get on a rectangular, very circular based. So we're going to go through a few examples and kind of just talk about the characteristics and things to look for here. So first one is what we call a cardioid, which if you look at it, it kind of looks like a heart, hence the name. With these guys, you're always going to see it in this format where it's going to be either r equals a plus or minus a, and then it could be sine of the angle or it could be cosine of the angle. Okay, and again, you don't have to not necessarily remember this, but you can also do remember this. It'll make these problems super easy. So when we look at these, you'll notice they're all kind of just rotations of each other. So what you want to think about here is if your cardioid, if most of it is on the positive x direction, which is what we have in this first case, it's going to be r equals a plus a cosine theta. So a and a would just be two numbers, but it's going to be cosine because it's horizontally based, right? It's sideways heart instead of a vertical heart. And then it's a plus because it's more on the positive side. So now using that same logic, you might be able to tell me, oh, well, this one's horizontally based. It's a heart that's sideways, but now it's more on the negative side. So now it's going to be r equals a minus a cosine. Crazy, right? All right, so now these ones are vertically based ones. So the only thing that changes is we use sine. And again, you want to think, okay, I'm mostly in the negatives in terms of the y values. So this one's going to be minus, and then this one, because it's mostly in the positive side, it's going to be plus. Okay, so again, don't necessarily think about like, oh, this looks like a heart, so it's positive. No, just think most of it's in the negative side of the graph, like bottom of the graph. So it's minus, and it's sine because it's a vertical based. Okay. All right, so there's cardioids. Now we're going to go to limacone with a loop. Okay, and for these ones, you're going to have two different values. So you're going to have an A and a B. And in this case, A is going to be smaller than B. Okay. And I guess one thing I should also mention with these is cosine. Not only like am I saying like the heart is sideways, but it's also the symmetry is over the x-axis for cosine, symmetry over the y-axis for sine. Say that here because it's kind of the same idea. So for these guys, it's very similar where you're going to have almost that kind of same heart shape, but now you have this loop in here. That's why it's a limacone with a loop. So it's got this inner loop. Wherever most of the stuff is, that's telling you what this equation is going to look like. So again, symmetry over the x-axis means it's cosine. Because it's more on the right than the left, you're going to say it's going to be A plus B cosine theta. For the second one, it's symmetry over the x-axis, but now it's mostly on the left, which means the equation is A minus B cosine theta. And then you'll never guess, hey, it's symmetry over the y, but now most of it's down below, so it's r equals A minus B sine of theta. And then this one, most of the action's above, so it's r equals A plus B sine of theta. And again, that's really all you need to know, is just how that pattern works. All right, so we had lemmasones with loops. Now we have lemmasones without loops. And this one ends up where you still talk about an A and a B value, and we're still going to say A is the smaller one, but now you'll notice the order is a little different. So you'll never guess, follows the same pattern that the bigger side is going to tell you whether it's plus or minus, and the symmetry is going to tell you whether it's cosine or sine. So the top two are cosine, and it's going to be plus for the first one because most of it's on the right, but now it's B plus A cosine theta. So the bigger number is first, okay? And here it's B minus A cosine theta. Crazy idea, right? And then now these ones, okay, ooh, we switched it up a little bit. We put the one that's more positive first. So we're going to say B plus A sine of theta. And then this one will be R equals B minus A sine of theta. So again, all of these patterns are all the same. These are kind of all in the same family. It's just whether these values are bigger, smaller, or the same than each other. So yeah, and then you have that symmetry over there. So there's those guys, the lemmasones and the cardioids. And then the last one we're going to talk about in this video are the polar roses. So these are the fun ones. They look like flowers, but mathematicians don't know their flowers very well, so they called them roses, even though they don't really look like roses. So with these guys, there's going to be a little bit more tricky of a pattern, but we're going to talk through this and you'll kind of see a lot of these patterns. So these guys are always going to come in the form of R equals A times either sine or cosine of n theta. Okay. And so that's how these equations are going to look. And what you're going to see, and actually, I'm going to actually write what these equations are first and then talk about the patterns. So this first one, its equation is going to be R equals 3 cosine 2 theta. Okay. You may be like, where did this come from? Like I said, I will talk about what the, 2 theta, what the patterns are here, and maybe you'll see them as we kind of keep going. This one is R equals 3 cosine of 3 theta. Okay. The next one is R equals 3 sine of 2 theta. And then the last one is R equals 3 sine, sine of 3 theta. All right, so what we end up looking at here, and like I said, it might be clearer with this pattern, is you'll notice they all go out to 3 circles. Well, that is actually telling you that 3, which is constant in all of them in the front, is telling us our length of the petal. And yes, we do call them petals in polar roses. So length of petal. Okay. All right. Then next thing to look at is the number on the inside. Okay. So here we had 2, ended up with 4 petals. 2 again ended up with 4 petals. But then we had 3 and 3 petals, 3 and 3 petals. What the pattern is here is when this number on the inside is even, if you double this number, so 2 times this number times n equals number of petals when n is even. So had that said 4 theta, you'd actually have 8 petals. 6 theta would be 12 petals, so on and so forth. But when n is odd, so when n is odd, n equals number of petals. Okay, so 3, 5, 7, that's telling you how many petals you have. Okay, and then the last thing is cosine versus sine. Well, cosine will always have a petal on the x-axis. So you can see here, petal on the x-axis. This one actually has 2 petals on the x-axis. That's how we knew it was cosine. And then for sine, you'll notice there is no petal on this axis, right? They're off the axis. They could be on the y-axis. You'll notice this one is here. But again, you will not have one on the x-axis, and it's 100% possible you don't have one on the y-axis, as we saw here. So that's how we know it's sine. Okay. But again, don't necessarily need to know all these patterns, but it actually makes these problems much, much quicker and easier if you do. So yeah, thanks for watching. Have a good day.